So fundamental theorem of calculus part 1 just tells us what's the derivative of an integral, which has a whole bunch of interesting things how we can figure that out and what it goes and other applications. But in a nutshell, all it is here, and I'll show you why. Here's the integral. Notice they have that dummy variable thing going on, and that's important. So what you do is the derivative of the integral is just the integrand times the derivative of the bound, that upper bound. And we'll show you some examples here in a minute and talk you through it. So let's get rid of that. Okay, so here's an example of what I did. So here's some function f. Maybe I should have written this as big F. So this is some antiderivative. Well, we know that the derivative of that number that function is just the constant 3. So if I wrote this as an integral, it would be the integral from some number, I wrote 2 just because I wanted to write 2, to x of 3. So how fast, so what's the derivative? So then if they ask me what's the derivative of that integral, well, it's just going to be this thing with find the antiderivative right there, but then we got to also ask ourselves what's the derivative of the dummy variable there, or that variable there. Well, the derivative of 1x is 1, so that's why that derivative is just equal to 3. It's how fast it's changing. Okay, so that's pretty straightforward. So here's another one. I worked it out. I actually did it out the long way, but let's talk about the shortcut. So what I did is, here's the thing I'm finding the antiderivative of. I replace that dummy variable with the x. So that is the actual answer to that. If I asked you to find what's d dx of that integral, you would just tell me sine x. Now, why? So what I actually did is I found the antiderivative. I did this a long way. I want you to do this first step. That's what I want you to do. But why does that work? So I found the antiderivative of sine t and wrote negative cosine t. Then I evaluated that. This is just using fundamental theorem part 2. I dropped in x, and then I dropped in 0, and I got that function. Now I want to take the derivative of that function. Well, the derivative of negative cosine x is sine x. The derivative of 1 is 0. So that's the derivative of that function, which is the derivative of that integral. Okay, so again, I don't want you to do this. I want you to use the shortcut. Okay, here's another one that I did ahead of time. Let's see. Oh yeah, this is where we got to worry about the dt. So we know, well, again, I did it out the long way. But I was hoping you see that the answer is this. Where does that 2 come from? Well, that 2 comes from because I have to find, dropping in the 2x here, but I'm also have to find the 2x here. So what I'm really doing is I'm finding d dx of 2x. Sorry, messed that one up. Lost my thunder. I'm taking the derivative of that upper bound, which is 2. Okay, because it's changing it more than just a constant rate or at a linear rate. I guess it's still linear, but it's changing a bit differently, right? So what I did to verify this is I found the antiderivative again, and then went from 0 to 2x, and I dropped in 2x into cosine t, and I dropped in 0 and got 1. Now if I take the derivative of this, well, the derivative of negative cosine is sine 2x, but then you got a chain rule going on. You got to take the derivative of the inside, all right? So that's where the 2 is coming from. And of course, the derivative of that constant is just 1. So it's just 0. So that's why I don't even have to worry about it. So the easy way to do this, take that number, drop it in there. You don't do anything with it. You leave it alone. But then you got to take the derivative of it to get that last thing. Okay, so here's nice. This is nice, right? We don't have to worry about. I see that it's just an x, so that whole taking the derivative of that doesn't matter. But see, even though I've got 2 functions, that's the product. We're just going to drop those in like that, and we're done. That's the derivative of that. So even though you don't know how to find that antiderivative, and we won't in this course, it requires integration by parts, and that's a Calc 2 kind of idea. So we won't worry about that. You'll see that in Calculus 2 if you do that. But you can take the derivative of it, and that's not too bad. Okay, so then I came up with this, and I didn't find the antiderivative because we don't know how to find the antiderivative of ln in this course, and you won't because that's integration by parts also. But we can take the derivative, so I replaced the p with a 3x squared, you see that? But then I got to take the derivative of that 3x squared, which is bring the 2 down in front and take away 1. So the 6x came from this piece, and then I just wrote the ln of 2 plus, and then 3x squared is 9x to the 4th, right? The mistake that people want to start doing is they want to start taking the derivative of the ln. You leave this part alone other than dropping in that variable, or whatever is there is what you drop in for the dummy variable, okay? So now what we've got is something with, we usually have the variable on the bottom. The variable on the numerator, and we don't. Now one of those rules, one of those integral formulas was if you have b to a of f of x dx, you can switch it to negative, b being the bigger number, you can reverse the bound limits of integration and just change the sign, right? We did some of that. And dx, so that's what that is. And then now, what do we get for an answer? Actually, we're going to go, so that's that, I guess. So now let's apply that idea back here. Here, let me erase this. So we're going to reverse those values, and I'm going to change the sign. So 0 to the square root of x, the sine of r squared dr. I'm going to drop that square root in there, so sine of the square root of x squared, but then I'm going to do the derivative with respect to x of the square root of x. Okay, I guess I'm doing the derivative with respect to r, aren't I? So the derivative of that, I don't know, does it really matter? So I'm going to drop in x's. So anyways, this becomes x to the 1/2. Use the power rule. Okay, so I'm going to get, and square root of x squared is x, so we're going to get sine x over 2 times the square root of x. And that's what the derivative of that integral, oh, and the negative, I lost the negative. Yeah, so that's that integral. Okay, so reversing those bounds of limitation, limits to limit integration, and changing the sign is a trick we can do. So then comes the tricky stuff. What happens when you have 2 variables and you don't have a number? Well, what you got to do, you're going to split that integral somewhere, and 0 is a nice place to split it, so why not? So I said, hey, I'm going to integrate this expression from x squared to 0, and then from 0 to x cubed. So the bottom limit to 0, and then 0 to that upper limit. And then notice that addition property for integrals, those have to be the same, so we could smush those together to get back there. So what does that do for us? Well, notice how we don't have the constant on the down in the lower limit. I reversed it, changed the sign. This one's all set. So we're going to drop in x squared in there. So I've got 2x squared, and then, of course, the derivative of x squared is 2x, and then we get the negative. So that's what this becomes, and this becomes, why do I have 2 pi? I think that is strange. I should have 2x cubed, shouldn't I? And then the derivative of x cubed is 3x squared. So that's what you've got to do when you get the bounds of integration of both variables, okay? You split it and then reverse the direction, reverse the sign of one of them and go for it. There's other videos that maybe do this in a different way, but I try to make this concise. You're more than welcome to go find those. Go get some practice now out of the textbook too before you jump in and try them out open math.